BioniChaos.com is a platform dedicated to the development of innovative biomedical data tools with a focus on interactivity, gamification, and accessibility. The website hosts a variety of web applications designed for exploring and visualizing complex biomedical data, making these tools accessible to both researchers and the general public. The EEG Seizure Detection Project is one such tool, providing users with an interactive platform to explore EEG datasets, visualize seizure events, and understand machine learning models applied to epilepsy detection. This tool serves as a resource for both educational purposes and research, enabling users to delve into the nuances of EEG data and replicate findings related to seizure detection. Future developments aim to enhance the interactivity of the tool, allowing for deeper data exploration and the integration of real-time analysis features. Overview of the dataset and research. The dataset in question is derived from the CHBM Scalp EEG Database, which contains EEG recordings from pediatric patients with intractable seizures. Converting their multi-channel EEG signals into rhythmicity spectrograms using short-time Fourier transform, STFT. The spectrograms serve as input for a generic convolutional neural network, CNN, to classify seizure and non-seizure events. The CNN model achieved an average accuracy of 91.89% on the training set, 88.17% on the validation set, and 61% on the test set. Data structure explanation. The dataset is organized into three main subsets: train, test, and val, each containing two categories, seizure and non-seizure. The images within these categories are spectrograms derived from EEG recordings, representing either seizure or non-seizure events. The structure facilitates training, validation, and testing of machine learning models. The explanation of this structure is based on both the research paper you provided and the data organization itself, which is standard for machine learning tasks in the biomedical domain. This structured organization ensures that the models can be effectively trained and evaluated, with clear distinctions between the data used for learning and the data used for validation and testing. This approach also helps in maintaining the integrity of the model evaluation process, providing insights into how well the model generalizes to unseen data. The structure you've provided outlines a directory with various files and subdirectories, particularly focused on EEG seizure and non-seizure image datasets. Here's how the structure is organized. 1. Main directory, data, contains a PDF, copy of the published paper.pdf, and an image, dataset details.png. The key content is within the EEG seizure and non-seizure image dataset directory. 2. EEG seizure and non-seizure image dataset. This directory holds another folder named Dataset, which is further divided into test, train, and val subdirectories. 3. Subdirectories, test, train, and val. Each of these contains further subfolders named non-seizure and seizure. Within these subfolders are numerous .png files representing images of EEG data, categorized by whether they are from seizure or non-seizure events. Selecting files for display. If your web application is focused on displaying specific EEG data, you would typically start by selecting images from either the seizure or non-seizure subdirectories within the test, train, or val folders, depending on the dataset split you are interested in, e.g., testing, training, or validation. In machine learning, datasets are often split into training, validation, and test sets. The training set is used to train the model. The validation set is used to tune the model's hyperparameters and assess its performance during training, and the test set is used to evaluate the model's performance after it has been fully trained. The images in the val folder would be used during the training process to validate the model's performance, helping to prevent overfitting. Dataset overview. The dataset consists of EEG recordings from patients with epilepsy, categorized into seizure and non-seizure segments. These segments have been processed into rhythmicity spectrograms, providing a visual representation of the EEG data. The dataset is organized into three primary folders: train, test, and val, each containing further subfolders for seizure and non-seizure images. 3. Cross-validation insights. Integrate functionality that allows users to compare images from different subsets, e.g., comparing test and validation datasets. This could help in understanding how the model's performance varies across different data partitions. 4. Model replication and evaluation. Implement a feature that allows users to replicate the results presented in the original paper using the provided dataset. This could include steps like feature extraction from the images, feeding these features into machine learning models, and visualizing the model's performance, e.g., confusion matrices, ROC curves. To implement a probability evaluation for the likelihood of seizure in the EEG images displayed on your web application, you can follow these steps. 1. Pre-trained model integration. Use a pre-trained deep learning model or train your own on the dataset to predict whether an image represents a seizure or non-seizure event. The model should output a probability value indicating the likelihood of seizure in the image. 2. Backend processing. Modify the backend, Flask, to handle image analysis requests. When a user selects an image, the backend should pass the image to the trained model. The model will return a probability value between 0 and 1, where a value close to 1 indicates a high likelihood of a seizure, and a value close to 0 indicates a low likelihood. 3. Display probability scores. In your JavaScript, modify the update non-seizure image and update seizure image functions to make an asynchronous request to the backend for the probability score whenever an image is updated. Display the probability score beneath each image, updating dynamically as users change the images via the slider. 4. Explainability. Add a brief explanation beneath each probability score to help users understand how the model arrived at the prediction. This could include information about the features or patterns in the spectrogram that the model found indicative of seizure activity. Example flow. 1. Model training. Train a CNN, convolutional neural network, or use an existing model trained on the same dataset. 2. Backend API. Create an API endpoint in Flask to accept image paths, run them through the model, and return the probability score. 3. Frontend update. Modify the JavaScript to fetch the score from the API and display it. Example display. Seizure image. Probability 0.85, high likelihood of seizure. Non-seizure image. Probability 0.10, low likelihood of seizure. To implement this feature, you'll start by training a simple model using the data in the train folder of your dataset. Here's how you can approach this. 1. Model training, data preparation. Load the images from the train folder, separating them into seizure and non-seizure categories. You might use a simple convolutional neural network, CNN architecture for this task. Training. Train the model to classify images into seizure and non-seizure categories. The output of the model should be a probability score indicating the likelihood that an image is a seizure. 2. Flask Backend. API endpoint. Create an API endpoint in your Flask app that accepts an image path as input, feeds it to the trained model, and returns the probability score. Serving model. Load the trained model when the Flask server starts and use it to generate predictions for images on demand. 3. Frontend integration. Modify your existing JavaScript functions to send a request to the Flask backend to retrieve the probability score for the currently displayed image. Display probability. Display the probability score beneath each image, updating dynamically as users scroll through the images. 4. Explanation in HTML. Model training summary. In your HTML, provide a section that explains the training process, including the architecture used, training data, accuracy, and any challenges faced. Interpretation guide. Offer a brief guide on how to interpret the probability scores, helping users understand what a high or low score means in the context of seizure detection. Example implementation plan. 1. Train model. Use TensorFlow, Keras, or PyTorch to train the model. 2. API setup. Modify your Flask app to include an endpoint like /predict, which takes an image path and returns the model's prediction. 3. Update JavaScript. Add functionality to request and display the prediction score. HTML explanation example. The model was trained using a CNN on 2,000 images from the dataset. It achieved 85% accuracy. The displayed probability score indicates the likelihood of seizure activity in the image, with values close to 1 suggesting a high likelihood. This approach will allow users to gain insights into the model's performance while exploring the dataset interactively. To implement the model training using the images in the train folder, you'll follow these steps. 1. Data loading and pre-processing. Load images. Use libraries like PIL or OpenCV to load images from the train folder. Since the images are already categorized into seizure and non-seizure folders, you can label them accordingly. Resize and normalize. Resize the images to a consistent size, e.g. 128 by 128 pixels, and normalize pixel values to the range 0-1 for better training performance. Data augmentation. Apply data augmentation techniques like random rotations, flips, and shifts to increase the diversity of the training data and help prevent overfitting. Tab 2. Model architecture. Convolutional neural network, CNN. Use a CNN model, which is well suited for image classification tasks. The architecture might include several convolutional layers with ReLU activation, followed by max pooling layers, and eventually fully connected layers leading to the final output. Output layer. Use a single neuron with a sigmoid activation function in the output layer to produce a probability score indicating the likelihood that the image is a seizure. 3. Compilation and training. Loss function. Use binary cross-entropy as the loss function, since this is a binary classification problem. Optimizer. Use an optimizer like Atom, which adapts the learning rate during training for better convergence. Training loop. Train the model for several epochs, monitoring the loss and accuracy on a validation set, potentially the val folder, to ensure the model is learning effectively. Chapter 4. Saving the model. After training, save the model to a file using a library like TensorFlow or PyTorch. This model will later be loaded by the Flask backend to make predictions. 5. Evaluation. Evaluate the model. Test the model on the test folder to measure its performance. Metrics like accuracy, precision, recall, and F1 score can be calculated to provide insights into the model's effectiveness. 6. Integration with Flask. API endpoint. Create a Flask API endpoint that loads the trained model and accepts image paths as input. The model will return a probability score indicating whether the image is likely to be a seizure. Serve results. Integrate this functionality into the existing web application, displaying the probability score beneath each image as users explore the dataset. This process will allow you to create a simple yet effective image classification model that predicts the likelihood of seizure activity in EEG images. In the next response, I will generate the Python code to implement this plan. Here's a brief overview of how the script is structured. 1. Importing libraries and loading data. The script starts by importing the necessary libraries, followed by loading the images from the dataset folders, train seizure and train non-seizure, resizing them and normalizing the pixel values. 2. Building the CNN model. It defines a simple convolutional neural network, CNN, model using TensorFlow Keras, which is structured with convolutional layers, max pooling layers, a flattening layer, dense layers, and a final softmax output layer for classification. 3. Training the model. The script uses data augmentation to generate additional training data on the fly, and then trains the model using the training data. Validation data is used to monitor the model's performance during training. 4. Saving the model. After training, the script saves the trained model to a file, seizure detection model.h5. 5. Evaluating the model. Finally, the script evaluates the model on the validation data and prints out the accuracy. To use this script, you can save it as a single Python file, e.g. trainmodel.py, and run it to train your model. The current conversation contains 48 prompts, including questions, requests, and responses. The relevance of code versus prompts in the next 5 years will likely depend on the context and the development of technology. While natural language prompts are becoming increasingly powerful with advancements in AI, code is expected to remain crucial for several reasons. 1. Precision and control. Code allows for precise control over software behavior, which is essential in many applications, especially in critical systems where accuracy is paramount. 2. Customization. Writing code provides the ability to customize and optimize solutions beyond the capabilities of predefined models or prompt-based systems. 3. Integration and interfacing. Code is necessary for integrating various systems, tools, and services, which may not always be possible through prompt-based systems alone. 4. Innovation and development. New technologies, frameworks, and software often require coding for their creation, deployment, and maintenance. While prompts may increasingly simplify certain tasks, particularly in automating and generating code, the underlying skill of programming is expected to remain highly relevant, especially in more complex or specialized domains. Therefore, while the role of prompts may grow, coding will continue to be essential for those needing deeper, more customized, and precise solutions. Taking the opposite view, it's possible that in 5 years, natural language prompts could significantly reduce the need for traditional coding. As AI systems become more advanced, they might handle increasingly complex tasks based on simple, human-readable instructions. This would make programming more accessible to non-developers, enabling anyone to build sophisticated applications without deep technical knowledge. The trend toward automation and AI-driven development could shift the focus from writing code to crafting effective prompts, essentially democratizing software development and innovation. The future of a website like BioniChaos.com would likely involve AI as an enhancement rather than a replacement. While AI could streamline content creation, automate interactions, and improve data analysis, the core purpose and unique offerings of a site like yours, especially one focused on biomedical data and gamification, would still require human insight, creativity, and domain-specific expertise. AI might handle repetitive tasks or provide advanced user interactions, but the vision, innovation, and specialized content you provide would continue to set your site apart.